Welcome to lesson 24, area. So we have spent the past few months or weeks in some cases studying differential calculus, and that kind of all came from looking, remember, at the tangent problem and the velocity problem. So we looked at limits of slopes of secant lines, and that all kind of led us to a derivative. We've spent a lot of time working through all of that. So we are now going to shift gears to the other branch of calculus, which is called integral calculus. And so we're going to do the same kind of thing, which is start by investigating a problem, a question that we have, and that will develop the mathematics we need to look at the other aspects of calculus. So let's start by talking about the area problem. How do we measure area? And we have formulas for specific shapes that we're aware of. And most probably basic would be our area of a rectangle is just length times width. And remember when you were in elementary school, it was kind of like you were adding up the one square. Each one of these squares would be like an area of one. It was 1 by 1. And so you're just adding up how many squares you have. And in a triangle, if you have a perpendicular height and base, then we also know that basically it's just half of the rectangle. If you put two of those triangles together, it would make a rectangle. So take half of it. That's the area of your triangle. But then when it comes to something like a circle, we know this formula, right? But where did it come from? How did that get developed? So Archimedes was actually the one who discovered how to find the area of a circle, and it was before pi was even a number. And what he would do is he would put inside of the circle polygons that had more and more sides. So I can draw maybe one, and then that's going to be the extent of my beautiful drawing skills, right? So here's I don't know how many sides that has, 6, 8, looks like maybe 8. And if we were to find the area of this, which we know how to do, because again, you can just break it into a bunch of triangles, then that's pretty close to the area of the circle. It's not quite all of it. And so what if we made it 10 sides or 12 sides? Each one of those little bits of area that's not getting counted by this polygon would get smaller and smaller. So that is actually how the area of the circle was first calculated. And this was called the method of exhaustion. And it does seem exhausting, doesn't it? But the reason it was called that is because the area of the polygon would eventually exhaust or use up all of the area of the circle. That's kind of a little fun mathematical historical fact for you. So moving further into the area question, how would we find the area of a shape like this? And when I say like this, I mean, if we take this curve to be one side of the shape and then the two axes to be the other side of the shape, right? Like, what is the area of this? And that is exactly what we're going to kind of investigate, is something similar to this, an area sort of under a curve. So we're going to start with an easier looking curve. This graph is y equals x squared. Okay. And we're going to look at the area between 1 and 2. So if you draw a line on your paper between vertical at 1, vertical at 2. So this area here, this region, okay, this is what we're going to be kind of investigating in terms of what is the area of this region. So under the curve, above the axis between these 2 points. Okay, so we're going to do a little Archimedes investigation, and we're going to look at that on the next page. We're going to kind of try to fill up this area with something we know how to find the area of, and that's going to be rectangles. So I'm going to try to zoom in here a bit because it's going to be a little bit easier to see. So I'm going to take this first well, let me look at it this way. It looks like there are 1, 2, 3, 4, so sort of 5 intervals between 1 and 2 here. So I'm going to make each one of those the base of a rectangle. So for my first rectangle, it's going to go like this. Okay. And I'm going to make the height be this endpoint on the curve. Okay. From the right side of the base of this rectangle. I'm going to take that right side up to the curve, and that's going to be the height. Okay. So this would be kind of like my area 1, the first rectangle. And I'm going to keep doing that for all the rest of them. So the next one, I'm going to make my base. I'm going to take the right side height up to the curve. Oh, looks like it's about there. And make that the height of my rectangle. And then I'm going to keep doing that. Area 3. So I have, oops, I was trying to make that a little smaller so I could see it. Area 2, area 3, keep going. Take that right side all the way up to the curve. Area 4. Oh, that is not a straight line. That's what happens when you try to go too fast, right? Never helps you out in terms of the straight lines. Okay, so area 4, area 5. Okay. So here I have, and I'm going to zoom out just a little bit so you can kind of see. And we've labeled this as an overestimate, and I think you can see why, because I definitely have all of the area in my region that we talked about. It's all there, included in the areas of area 1 plus area 2 plus area 3 plus area 4 plus area 5. But then I also have this extra, extra area in each one of these rectangles that comes over where the curve is. Now I feel like I'm just coloring, which is kind of fun. It's easier than calculus. All right. So in this case, I have, right, the extra area is in this green. I've colored it green. Okay. And that's why it would be an overestimate if we were to add up the area of these 5 rectangles. Okay. We're going to have too much area. Okay. So what could we do to maybe make it less area? I'm going to come over here to the underestimate. Nope, I'm not. Yes, I am. If I zoom in, I think that's the way to do it. Okay, so this time I'm going to draw those same bases of my rectangles. But now I'm going to make the height the function value on the left side. So before we used this side and came up to the function. Now I'm going to use the left side and come up to the function for each one of these. So you can kind of see it taking shape. As such. Okay, so I still have those 5 rectangles. And I can still add up the area, but now I'm not actually going to get all of the area that I'm looking for, right? I have these places here that are not counted by adding up the area of my 5 rectangles, but are in fact part of the region we're trying to find the area of. So that's why we would label this an underestimate. And we have the missing area, right, in red below. For both of these, we could actually calculate the areas. I mean, for each one of these rectangles, what is its width? I mean, the whole width from 1 to 2 is 1, right? And how many of these rectangles do I have? I have 5. So my width for each one of these looks like it would be 1/5 or 0.2, which would be the same over here. And then the height is going to be a little different. Oops, I can't spell height. I think that's better. So in this case, we use the function value, and what we call that is the right endpoint, and meaning the right endpoint of the base of the rectangle. And so over here, the difference is now the height is the function value, the y value, right, at the left endpoint, because we use the left side. And those are pretty common things that we'll see as we move a little forward using left and right hand endpoints. Another thing we could do, I mean, it doesn't have to be the left or right hand endpoint. I mean, maybe what we do instead, and again, I'm going to try to zoom in a little here, is we use the point kind of right in the middle and then come up to where that hits the function and make that the height. So I'm going to just draw my heights in here first, kind of trying to go right in the middle of that, each one of these tick marks or grid lines, right in the middle, and see if I can sort of identify where that function value is. About right there. So if I were to turn those into actual rectangles, you can see them taking shape. And now, I mean, I guess we would say that this is probably a closer estimate than the other two were. I have both overlap and missed area, right? I have a little extra here, but I have a little missing part there, another missing. So less missing, that's for sure. And a little less overlap. And since I have both, you would imagine there's some level of them canceling out. It's not going to be perfect, right? But so just visually speaking, that seems like it would be closer of an estimate using 5 rectangles. And, you know, like I said, here we can actually calculate the area of each of these 5 rectangles. So in the first one, the one where we use the right hand endpoints, we're going to call that R sub 5 because the R stands for using the right hand endpoints. And so each one of them will have a width of 0. That doesn't look like much of a 0. Let's see if I make this a little bigger. If we were going to actually calculate the area, I'd have 0.2. And then I need to find the height. So what I need to do is figure out what this point would be. If it's 0.2 away from 1, it'd be 1.2. And then I need to plug that into the function. Remember, the function is right, y equals x squared. So when I plug that into the function, that will give me the y value, which is the height of this rectangle. And then I'll plug in the next one, which would be 1.4. I plug it in, I'm going to square it, etc. So if I'm just kind of writing that out down here, my first height would be 1.2 squared. And then my second rectangle, I have the width and the height would be 1.4 squared, 1.6, 1.8, and the very last one is that 2 squared. And we could, you know, run the number and figure out what that was. So same idea for the next one. We're going to call the next one L5, the one where we had an underestimate because we were using the left-hand endpoints, so L5. Same widths, but now my height will start with the 1 squared, then the 1.2, 1.4, 1.6, and 1.8. So I'm not going to be using the 2, but I will be using the 1 instead. So just writing that out. All right. And then last but not least, what about the midpoint? So my width is still 0.2. And in fact, I could put that out front and then just sum up all of the heights inside, couldn't I? As a slightly less writing, I suppose. And so what value am I plugging into the function now? For each one of these, it's what's right in the middle. So this was 1 and 1.2. So in the middle would be 1.1 and 1.3 and so forth. So 1.1 squared, 1.3 squared, until my very last one was 1.9 squared. And that gives me using the endpoints. Okay, so the question that I want to ask before we turn the page is, how can I make any one of these more accurate? How could it be closer to the actual area of this region? And I'm hoping you said more rectangles. Okay. We're going to want to increase the number of rectangles. Obviously, if you have 5, which we had in this picture, you know, the width of each one of these overlaps is pretty big, or missed areas. But if I were to have 10, then this rectangle would be narrower and it wouldn't have as much area that it's over counting or under counting. So in this next picture or series of pictures, I've started with if from 1, oops, let's do this, 1 to 7. So we kind of have this function both above and below the x-axis, sort of looking at what is the area of these regions. And oops, you can see in these pictures that if I started with 10 rectangles, which is more than we started with in our last examples, it's kind of a pretty bad estimate. I'm missing all kinds of area here. I got a lot of overlap there, missing a bunch. So if I even just double that to 20 rectangles, look at how much more accurate. I'm definitely missing less of these areas, and my overlap is not nearly as abrupt, right? So increasing it, think of if I had doubled it even one more time, how much more accurate that would be. So now that we know something about limits, where do you think we could be headed with this? How could we make it the best accurate, most accurate, I guess, estimation of all? We basically make the number of rectangles go to infinity. So it's like you're making the width of each one of them go to 0. So they basically end up being just like straight lines. And then you're just adding up like the length of all those straight lines to get an area. That is where we are headed. So we are going to estimate the area using n rectangles, and then we're going to take the limit as n goes to infinity.